Okay, so here we are discussing the next topic, operation of a BJT. In a BJT, we have three regions, the emitter, and in the center we have the base, and the other one is the collector. So we know when we have two junctions, when we have a PN junction, there will be a depletion layer formed in between them. So here we have two depletion layers. Okay, we have a depletion layer between the base and the emitter, and we have depletion layer between the collector and the base. So what we are going to do is we are going to forward bias one of the junction and reverse bias the other junction. So here we forward bias the base emitter junction. We forward bias the base emitter junction. To forward bias the base emitter junction, we need to connect a voltage source. So we need to connect a voltage source where the positive terminal of the battery is connected to the P region and the negative terminal of the battery is connected to the N region. Now, the PN junction between the base and the emitter is forward biased. Next, we are going to reverse bias. We are going to reverse bias this collector base region. So we have to connect the negative side of the battery to the P region and positive side of the battery to the N region. So it will be like this. By doing this, by reverse biasing the collector base and forward biasing the base emitter, what are we trying to achieve? The idea is simple. This base region, the base region is very small. This base region is very small compared to the collector and emitter. So it is a very thin region. So when the base emitter region is forward biased, the depletion layer between this junction disappears. The depletion layer between base and the collector broadens because we have reverse biased it. Okay, because we have reverse biased it, it will broaden. And the electric field is in this direction. I hope you all can remember that. Okay, the electric field is in this direction. In the emitter, we have more free electrons because it is heavily doped. Can you remember the order? Emitter is heavily doped, next collector, and finally base. Because this emitter is heavily doped, we have more free electrons. And these free electrons starts to move into this base region. These free electrons starts to move into the base region, but this base region is very small. The base region is very small. So if the electron moves a little faster, they will eventually end up in this strong electric field. Okay, if they end up in this strong electric field, they get pulled into the collector region. Still, some of the electron who doesn't gain much energy or much speed can leave through this base region. Okay, if we show it using a single arrow is like this. A lot of electron will move into the base region. Some of them will leave through the base. A small amount will leave through the base. And most of them will end up in the collector. So did you get the reason why this is happening? Did you get the reason why? So this is the electron. Sarah and Shaham are clear. Or shall I go through it once again? What is happening? I'll relate it with a story. Okay, I'll relate this one with a story. Now, I'll relate this with a story. After that, let's go back to this, okay? A person wants to travel from a city A to city B for his interview. Let's say for his interview, he wants to go from city A to city B. Okay. Then he goes to the bus station to get the bus, but he misses the bus. So he has no any other choice but to take the train. So that's the time bus. Let's say now he has to take the train. When he went to the station, there is a train that is leaving, but the train goes to station C, which will pass B, but won't stop at B. Okay, that train won't stop at B. It will stop at C. So anyhow, the station master said, you just go running to the train. Okay, go running to the train and get into the train. This train anyhow will slow down. It will slow down at station B, so you can quickly jump out, so you can get down there. Okay. Although this train goes to station C, when it passes station B, it will slow down, so you can get down there. So now this person's idea is to get from station A to station B. Okay, that is his idea. So listening to the station master, he runs towards the train. Those inside the train pulls him in. Okay, those inside the train pulls him in. Now he is in the train. When he is close to station B, he gets down. As the station master mentioned, he gets down. Okay, but when he jumps out, can he just stop at once? No, right? He has to run for some distance. Then those who are in the front box, thought this person wants to get into the train, so they pulled him back into the train. So now he cannot get down. He has to go to station C. Okay, the station, the train will now stop once again at station C. So his idea was to get down at B, but he ends up at C. Okay. Now let's relate this story to this. This electron over here actually wanted to cross this boundary and get out of the base. Okay. But because it had more speed, it eventually ended up in this electric field. This electric field pulled it to the other side and left it in the collector. So is the idea clear now? You don't need to know what is going to happen after this. For now, you must understand the electron actually wanted to go to the base. It wanted to get out of the base, but due to its speed, because it had more speed, it ended up in the electric field where the electron gets pulled to the other side. Have you all got a rough idea about what's happening here? Did you get the idea? So now we have marked the movement of electron, right? we have marked the movement of electron. The electron from the emitter goes in. So here in this direction it goes in. If I mark the current will be outside. The electron is in this direction, and if we mark the current, it is out. We show it as emitter current IE. Here, the electron comes out of the base. The electron comes out of the base, and that means if we mark in terms of current, it is going into. So that is IB, base current. And here, the electron comes out. So we have to mark the current in. That is IC. Now let's look at the names. Why do we call this one as emitter and this one as collector? Look, this region emits the electron and this region collects the electron. So that is how they got their name, emitter and collector. Okay. So draw this diagram. And let me let's write the note below. This value has to be, this V has to be greater than 0.7. Now, if the base emitter region is not forward biased, will all of this happen? No, right? If base emitter is not forward biased, electron cannot diffuse from the emitter to the base. So none of this will happen. For that, we must have a voltage supply. We must first forward bias this. Therefore, V has to be greater than 0.7. And by Kirchhoff law, IB plus IC is equal to IE. Since you have noted the diagram, remember. Okay, done. Ah, below write down base emitter region. Base emitter region is forward biased. Is forward biased and collector emitter region. Sorry, collector and collector base region is reverse biased. The forward bias, the forward bias at the base emitter region, base emitter region allows the flow of electron from N to P region, from N to P region, flow of electron from the N to P region by depleting the depletion layer, or by depleting the depletion layer. Right. Yeah, depleting the depletion layer. Next, a large number of electrons, a large number of electrons are drawn across the base collector region, base collector region due to the setup, strong electric field. Strong electric field. a small amount of electrons flow out of the base. A small amount of electron flow out of the base. The above operation establishes the base current IB, collector current IC, and emitter current IE. According to Kirchhoff law, according to Kirchhoff's law, the current is added, right? IE is equal IB plus IC. But from the operation, we understood that the IB current is very small. There is only a small amount of electron that will leave. So if this is 100%, only 2% makes up the IE current. The remaining is IC current. The remaining 98% is the IC current. So sometimes we can consider that IE is almost equal to IC. Okay. Next topic, configuration. Next topic, configuration of BJT. Configuration of BJT. So we can use the BJT in 3 different configuration or 3 different connections. So there are 3 different connections. The first one, we give input between two terminals and get the output at the other two terminals. So here in this setup, this is the emitter, this is the emitter, this is the base, and this is the collector. So here the direction of arrow will show you the emitter also. Okay. Now we give the input. We give the input between the base and the emitter, and we get the output between collector and emitter. So here for both input and output, this emitter is common. Emitter is common for input and output. So we call this as common emitter configuration. Common emitter configuration. Or otherwise, or CE mode, or CE mode, common emitter mode. The second configuration, that is base, common base. So for input and output, we have the common base. We give the input between base and emitter. So this is the base, this is the emitter, this is the collector. We give the input here and get the output between collector and base. So this is known as the common base configuration. Common base configuration, or CB mode. And the other one, so here emitter is common, here base is common. The other one is going to be collector, common collector. I'll draw on the user kit. So in common collector, we give the input between base and collector. We give the input between the base and the collector. So this is the collector, base, and emitter. So here the input is given between base and collector, and the output is obtained between collector and emitter. So this mode is common collector mode. Sorry, common collector configuration, or common collector mode. So here we will be only discussing about common emitter. Okay, we will only be discussing about common emitter mode. Have I drawn this? So next subtopic, gains in common emitter configuration. Gains in common emitter configuration. First, current gain. Current gain. We use a symbol beta. So current gain is equal IC over IB. Collector current over base current. This is very much greater than 1. Second, voltage gain. Voltage gain. So voltage gain Vg is equal output voltage over the input voltage. So output voltage is obtained across a resistor in the collector. Okay, we will discuss later what is RC, and then we have IB, RB, base resistor. So IC over IB, that is beta, RC over RB. Again, this is also very much greater than 1. Next, we have power gain. Third, power gain. So PG is equal power output over power input. We know that power is V into I, right? Power is V into I. So that is VCIC over VBIB. So this is equal, instead of VC, I can write IC squad RC over IB squad RB. So this one could be written as beta square RC over RB, which is also greater than 1. So in a common emitter mode, all current, voltage, and power are gained or amplified. Okay. The power, there's a current gain, there's a voltage gain, everything is greater than 1. Therefore, this is the most preferred configuration. Have I noted this? In common emitter, in common